about another one of us as hobbies, which is the quantum effect. And our first speaker is Yuval Gefen. He's going to tell us about a new paradigm for edge states in the fractional domain.
So I'm delighted to be here, and I'm glad to see you are surviving to all these talks. I hope you survived mine. And I went through this transition from being a 50-something to 60-something recently, and I would like to share with you two insights. First, the good news. It happens only once. And second, the bad news, it happens only once. But we will take it easy because 60 is the new 59, so you have another year to go. And what I'm going to tell you today has to do with the tunneling of anyons, a certain class of exotic anyons. And preparing my talk, I recall an old work by Asa, which dealt with, I hope you remember that, which dealt with tunneling of anyons and electrons. So in some sense, it has influenced the project I'm going to tell you about. And I hope there is going to be a backlash, and I hope that this is going to influence you to get back to this topic and continue to produce excellent work in this direction. So specifically, this project has two layers. On the experimental side, this is the effort of Ron Sabo, Itamar Gurman, Amir Rosenblatt, Fabienne Lafont, and the rest of the team of Heiblum. On the theory side, this is a collaboration with my postdoc, Jilong Park, and Bernd Rosenau. So the story I'm going to tell you starts with the structure of the edge of composite fractional quantum Hall systems, and the specific example I'll discuss is the nu equals 2/3. And what I'll do here, I'll report telegraphically about certain aspects of recent work by John Hui Wang, Yigal Meir, and myself, and you will hear a detailed and deep discussion of that in the talk of Yigal tomorrow. But then I'll tell you about some experimental surprise that came up, which seemed not to be a missing part of the picture that was proposed by Yigal Meir, Wang, and myself. I'll discuss the experimental surprise, and then I'll show you a mock theory of how to resolve it. And I will not have time for the real theory, but I'll report at least the results of the real theory. So let me start with something simple. And this has to do with the edge of a simple quantum Hall system. For example, nu equals 1/3. So y is the coordinate perpendicular to the edge, and the edge has a chiral getless mode propagating in the direction of a semi-classical skipping orbit. We call this direction downstream. The location of this chiral mode is given by the profile of the Finnick fraction. This corresponds to the gradient between the bulk value, which is 1/3 here, to the value outside, which is 0. So this is simple. Now, when one goes to more complicated fractions, Hall conjugate fractions, meaning nu between 1/2 and 1, the structure at the edge is more complicated. And for our specific example of 2/3, it has been proposed in the early 1990s by McDonald that there should be two chiral modes, two counter-propagating chiral modes, 1 and 1/3, which correspond to a profile which goes non-monotonically from the bulk value 2/3 to the value outside, which is 0. One prediction of this model concerns the two-terminal conductance. So if we take such a system and couple it to two reservoirs at different chemical potentials, here the chemical potential is mu plus EV, and here it's mu, the prediction of this model is that current is carried by, from left to right, is carried by this mode, which is 1/3, and this mode, which is 1. Adding the two contributions together, we get a conductance, dimensionless conductance, which is 4/3. This is very nice, except that this value has never been measured. The universally measured value is 2/3. So the question is how one can construct a theory that will give value different than 4/3. And one idea is to introduce interactions, and this would be the bosonic action for such a model. This is the part that describes the mode, the channel 1. This describes the counter-propagating channel 1/3, and this describes density-density interaction between the two channels. Since the action is quadratic in the bosonic fields, it can be diagonalized, and we can find the eigen modes of the system. And the two-terminal conductance is given by this expression where delta depends on the velocities of the bare modes and the value of the interaction. And this is exactly the problem, because delta depends on non-universal values, and therefore the prediction here depends on small details of the system, certainly not in line, not consistent with the reported universal value, which is 2/3. And then came a seminal work by Ken Fisher-Tuczynski back in 1994, a really elegant work in which they proposed to incorporate both the effects of interaction and disorder at the edge, disorder which allows tunneling between the two modes. And the result was that if the interaction is sufficiently strong, which corresponds to this parameter delta being smaller than 3/2, disorder becomes relevant, and upon the application of a normalization group, the system flows to a new fixed point which underlies the universal behavior of this system. And at this fixed point, this stable fixed point, there are new eigenmodes. So instead of the bare modes, which are described by the bosonic fields phi1 and phi 1/3, we have new modes, which are described by the bosonic fields phi c, a charge mode, and phi n, a neutral mode. So pictorially, instead of having two counter-propagating modes, 1 and 1/3, we have downstream 2/3 and upstream a neutral, which is good news, because that would account for the universal value of the robust value of two-terminal conductance, 2/3. The theory also predicted the presence of upstream neutral modes, and it took 16 years before experiments by the Heidelberg group and by Amir Yacobi, the presence of those modes has been discovered. However, there were several lingering problems. Some other major experimental results were not explained, and that will be discussed by Yuval tomorrow. And it was clear that another model was needed. And that model relied on an earlier work by Yuval, which stipulated that when the confining potential at the edge becomes flatter and flatter, softer and softer, the profile, the filling fraction profile at the edge becomes more complicated. At a certain point, it has this structure, and this structure supports 4 chiral modes. 2 modes, 1 and 1/3, which move downstream, and 2 modes, 1/3 and 1/3, that move upstream. So then came the idea to follow the footsteps of Ken Fisher-Koczynski and incorporate both interaction and disorder, trying to normalize the system. Again, I'm skipping details. What is important for this talk is that this normalization is done in 2 steps. First, we consider these 3 modes here, which are normalized. We leave untouched the outermost 1/3 mode. And this gives rise to an intermediate fixed point. If we incorporate also this mode here, we'll get further another low temperature fixed point. So let me focus on the intermediate fixed point. And the intermediate fixed point, these original channels are going to be normalized to these channels. So the emerging picture is that we have a downstream 1/3 and another downstream 1/3 and 2 upstream neutrons, which is good news for several problems, several reasons. But the 2 main reasons, or 2 of the 4 main reasons, are that this model predicts also upstream neutral modes, which have been observed experimentally, and also this model will predict that if we pinch off the system and measure the 2 terminal conductance, one will observe a conductance plateau at 1/3, which has been observed experimentally. But everything looked fine, looked okay, but there was one important nagging problem that remained unanswered. And let me try.
Is that intermediate fixed point stable in some range of parameters?
I mean, as long as you forget about the outer mode, the outermost node, this is a stable fixed point. Now, if you introduce the weak tunneling to the outermost, then the whole system will flow to the real stable low temperature fixed point.
And are there other ways you might have combined modes? Is this one choice out of many, or is this the only way that can be?
I mean, in principle, you can combine in different ways. You can combine 2 and 2 and so on. But the reason why one does it is, first of all, there are reasons to believe that the outermost is further away than the other 3. And secondly, this picture turns out to give consistent predictions. Predictions are consistent with experiments.
Could you imagine that on the edges of something else they might combine differently and produce different?
I could, in principle, if you allow me to design my own potential, I could design a system that, well, for example, the 2 outermost 1/3 will be next to each other. And in which case, 1/3 and 1/3 with tunneling will localize. So I could invent other things. But they will be artificial. So the lingering puzzle has to do with noise. This is the subject of what I'm going to discuss. So this is the picture, the schematic picture of these 4 modes at the edge with a constriction, with a quantum point conduct. The solid lines are the charge 1/3 channels that take you, for example, from this source to this drain or this drain. The dashed lines are the upstream, the counter-propagating neutrons. So here we have a situation where one charge mode is fully transmitted and one is fully reflected, giving rise to a conductance plateau at 1/3. So half the current injected from the source arrives at these drains. The conductance between S and D is 1/3. This is nice. But what the nagging result is that when one measures the noise here, it turns out that there is noise, there is short noise on the plateau. And let me first show you how it looks like. One measures the noise spectrum as function of the applied voltage and obtains this line with a slope of 2/3. So there is a noise, short noise with final factor of 2/3. Why is this surprising? In order to understand why this is surprising, let's go back to history, to a simple picture that has been introduced by Landau for transport in 1 week. So here we have an impinging beam of electrons, which is noiseless. It impinges upon a barrier whose transmission probability is T. And then some of the electrons are scattered back, some will be transmitted. So the beam on the right-hand side of the barrier is stochastic, is noisy. And the short noise of the resulting short noise is proportional to T, the transmission probability, times 1 minus T. The proportionality constant involves E star, which is the final factor. So this result suggests that when we have channels which are either fully transmitting, T equals 1, or fully reflecting, T equals 0, the noise will be 0. And here, in the setup that I showed you just half a minute ago, we have 2 channels. One is fully transmitted, one is fully reflected, so you would expect short noise 0. This is one part of the puzzle. The second part is, even if we accept the fact that this short noise is 0, how come that the final factor is such a nice quantized number, and following on that, how come that this value is not the value of the underlying anyons? The underlying anyons will be 1/3, and here we obtain 2/3. Moreover, I'll show you that one can take the same bulk Philip function, 2/3, and have a slightly more complicated geometry, for example, 2 constrictions, and then come by other simple but different values of final factor. For example, 1/2, which is certainly not the value of the underlying charge. So what is the expansion of all this? Before I go to the physical picture, let me devote 1 minute for definition, for definition of the quantities that we play with. So this is the structure. We have two charge modes and two counter-propagating neutral modes. And I'll denote the respective excitations on these channels by the following names. Elementary excitations on the neutral modes will be called neutrons. Elementary charge excitation, this charge 1/3, on this charge mode will be called quasi-particle of 1/3. Elementary excitation on this charge mode will be called chargon. Why do I distinguish between an elementary excitation on this mode and an elementary excitation on that mode? The reason is that here, creating a charge is entangled with creating a neutrons, which is not the case here. In other words, if I define the respective bosonic fields like that, a process of tunneling a quasi-particle from the outer mode to the inner modes will involve the destruction of quasi-particle here, and turns out the creation of a charge on here, accompanied by the creation of two neutrons or two anti-neutrons. This is an example of a tunneling operator, and all in all, we have 6 equally most relevant tunneling operators in the game. Here I gave examples of 2. The symmetry of the problem is SU3, so actually it's a Pullman's QCD for solid state practitioners. So once we have this, once we understand that the tunneling of quasi-particle is associated with the generation of 2 neutrons, let's go to the real physical system. So this is our source. These are 2 drains, D1 and D2. Here we emit current to these 2 charge channels, which have an elevated chemical potential. So they flow in parallel, but at this point, one of those charge channels is backscattered. This one continues here. This one continues here, and it finds itself flowing in parallel with a cold channel, a channel with a lower chemical potential. And since there is some tunneling between the 2, the one with the elevated chemical potential would like to equilibrate with this one. And this equilibration will be accompanied by tunneling of quasi-particle from here to here. But as I told you, a tunneling of quasi-particle from here to here will involve the creation of 2 neutrons or antineutrons. Now, these neutrons being created move upstream along the neutron channels. But at some point, they would like to annihilate. And they can annihilate stochastically by to either a pair of a quasi-hole chargon or a pair of quasi-particle anti-chargon. For example, they annihilate, and this pair moves in this direction. So the charge we collected D2 for this event was quasi-hole. But on another event of annihilation of neutrons, we might have collected the quasi-particle. So all in all, we'll have here a currentless noise. The average current that we measure here due to this process of annihilation of neutrons will be 0, but that will be noisy. Now, if we assume that these channels are sufficiently long such that everything that wanted to equilibrate will equilibrate, and then we assume that all the neutrons pairs that were created did self-annihilate, then simple calculation will show us that the noise comes with a quantized final factor. One can repeat such arguments for more complicated geometry, as I said. I mean, this geometry has two quantum point contact, and the final factor we measure is different. It will depend on which of the terminals we bias and in which terminal we measure the noise. So
when you say final factor, you mean the E star, or do you mean the T times 1 minus T?
okay. I give you T, and therefore you know also 1 minus T. So I divide the noise by the voltage T, 1 minus T, and then I get this E star.
It's 2/3, or what's?
No, so in the, I'm showing you momentarily a table. So for the single PVC, it was 2/3. Here, there is a whole zoo of things, depending on which terminal you bias, which terminal you measure. But before I show this will be the next constancy. Before I show this, let me recap, and to recap the idea, I would like to resort to a very loose analogy with a classical fiction. So imagine that I have two canals, two aqueducts that lead water, but one has an elevated water level as compared with the other. Now, if we allow water particles to jump from this canal to the other, these guys will gladly like to equilibrate. But now we recall that, mechanically, that this hopping of water particles from here to here is also accompanied by the creation of neutrons that will move upstream and eventually inhibit and create noise. So the cycle here is that the charge equilibrate, creating neutrons, and these neutrons annihilate, creating noise. But it is a bit more subtle than that, because the equilibration, even when the two aqueducts on the average equilibrate, there will be fluctuations in the interface, in the water surface of the individual aqueducts. So locally, the water level of this aqueduct may be higher than that, which will allow further tunneling of water particles from here to here. So actually, there is a second hierarchy to what I described, namely charge equilibrated, created neutrons. These neutrons created noise, and this noise allows for further charge equilibration, which further introduce the neutrons, and they further introduce the noise. So this is I discussed the single QPC, the single constriction. There the theory fits with the experiment, and here there are other setups where we can bias different terminals and collect the current and the noise at other terminals. These columns, here, here, and here, are the experimental final factors, and those factors that are explained by this theory are marked here. There is an exception. We were not able to account for these 3/4. We don't understand why, but these cases have been accounted by the theory. So this is where we stand now. There are, of course, other things to do with other Finnick fractions, and it's very intriguing to repeat it for non-abelian systems, but I don't have anything to report on that at this point, and I would like to wish you again a good evening.
So, Yuval, can you explain in simple terms, how can you measure charge noise, right? That's what's been measured, voltage fluctuation. How do you measure anything neutral? I mean,
No,
neutral
no,
particles will not produce anything neutral.
no. So what I'm essentially saying is that the neutrons are only a mean, an intermediate step in the creation of a charge. So there is some equilibration process that generated the neutrons. Now you take such neutrons and
So
they
let's say,
direct
just
to
for an analogy, you can think of phonons in the side, right? Neutrons
But neutron has, it's not phonons in the sense that, I mean, they contain no charge, but contain quantum numbers. And all these tiny operators are based on discrete quantum numbers, conserved quantum numbers of these neutrons. So these neutrons are not just plasmons. But once these two neutrons annihilate, they create quasi-particle, quasi-hole, or quasi-hole, quasi-particles. And it's this flux of quasi-particle, quasi-hole that goes to some, is driven to some drain, and this is the noise to measure. So it's like in elementary particles. You annihilate two neutral elementary particles, and there is a flux of negative or positive in this direction, and this flux is completely random, so you measure noise without any average count. You don't measure directly the neutrons. You measure the product of the annihilation.
So, presumably, what you described is for spin-polarized electrons.
Spin-polarized electrons, yes.
So, the two-thirds state has also a spin-neutral.
Good question, I don't know.
Did you calculate?
I know something, so I'll tell you what I'm proud.
Did you calculate the tunneling density of states into such an image?
The tunneling density of states.
Right. What would I see? What would be the IV curve when I tunnel into such a image?
Okay, so good. So in principle, you can think of the following experiment. Suppose I have this complex edge, 1 and 1/3, and then next to it, I put, for example, I don't have a black hole. I put next to it a quantum hole of field function 1, and the three edges, that of the 1 and that of the 1 and minus 1/3, are moving parallel, and I have some tunneling, and like the old experiments of Amir, I'm trying to tunnel an electron from one to the other. Now, I can play all the games in the famous works of Amir, bias one with respect to the other, or gauge bias by putting flux, and obtain the momentum preserving tunneling from one edge to the other. And this work has been worked out by Glasman, his postdoc Meyer, and myself a couple of years ago. It's an interesting structure.
What's the answer?
It's not one well. I mean, there are different curves with different structure that are indicative of the various features of
Let
time.
me put the question in the following manner. In the late
Can you
90s,
speak up?
in the late 90s, there was measurement by Chung and his students, and what they basically found over a large range of filling factors is that the exponent, the tunneling exponent, goes roughly like 1 over nu, where nu is the filling factor. Does this, takes you in, towards such a behavior in any way?
No, I mean, I think that what they discussed was not tunneling, a momentum preserving tunneling,
Right.
was point like
Right.
tunneling.
Right.
And I think that the answer is more detailed, because you need to tell me to make some assumption about how my tip is coupled differently to the 1 and to the 1/3. So one of the games that we are playing now is to take the 1 and 1/3, which are coupled to interaction and so on, and try to separately bias the 1 and the 1/3 and see all kinds of IVs. But these are details. I cannot tell you yes or no.
I just want to make sure I understood. So for the 1/3 case, the T1 minus T is not really correct, right? Because in one limit, where T is small, is often quasi particles are tunneling, where 1 minus T is small, it's electrons tunneling. So in your case, do you have a situation where
No, but in the 1/3, in the analog of that, in the 1/3, we, mind you, we have a situation where each channel is either fully transmitted or fully reflected. So the analog for the 1/3 will be a completely open system or completely closed system. I'm not talking about short noise when a channel is partially transmitted, partially reflected. That will be more complicated. I'm talking about a clean case where you are really in a plateau. So to be in the 1/3 to be in the plateau means that the system is fully open.
Just a dumb question, I just want to make sure I'm oriented, but the role of disorder in this is these channels would be protected from equilibrating with each other if momentum was conserved, and you just need the disorder to violate momentum conservation.
So I didn't get.
You tag the role of disorder in equilibrating the different channels and producing a neutral node. That's because if momentum was conserved, these channels wouldn't, you just have to buy the quadratic couplings. You need that to violate momentum conservation.
Yeah, I mean, if I didn't have this momentum destroying conservation, I would need to play both with the relative voltage and also the flux enclosed between the two, which further shifts the momentum in order to find some specific points where this tunneling will be possible. But here I don't need to worry about it.
Okay, so let's think about it again.